is also not the best. But so anyway, so there is at least one advantage in presenting the techniques to synthesize molecular knots from a historic perspective, like I will do, is that, of course, people started to think about the synthesis of knots in relatively simple ways, synthesizing relatively simple molecules. And then as time went on, the techniques to synthesize molecular knots became more and more sophisticated, as you can imagine. And so presenting this research area from a historic point of view has the benefit so that we can build together complexity from one slide to the other. Another advantage is that the idea of building knots with molecules originated quite early on time, if you may say, and actually coincides with the birth of modern knot theories. And this starts in the late 19th century, 1867. This is our year, and the story involves three protagonists, some of which you're probably very well familiar with. The first one is William Thomson, that's known under the name of Lord Kelvin. We've already heard about him in the past days because he's the one who gave the definition of chirality. At the time, very well established chemist and physicist. The other two guys are a bit younger. One is a mathematician, Peter Tate, and the other one, as you all know, of course, as a physicist, James Maxwell. The three men are all from Scotland, so they know each other. They've met each other, and they actually exchange regularly through letters. They didn't have emails at the time, of course, and they exchange on all kinds of topics of interest. And one of the topics of interest at the time is the atomic structure. It is clear at that time that atoms exist, but of course, how they are constructed is a big question mark. And Lord Kelvin comes up with this theory. Well, it's not so easy.
If it's distance dependent,
yeah,
so it's tries on this side.
Easier. Okay, I'll stick on this side now. So it comes up with this idea that since matter is supposed to be immersed into ether, which is kind of the version of space at the time, then maybe this ether may form vortices, tubes of vortices that could get entangled, and therefore atoms would be knots of this vortices. And this theory has many advantages in explaining some of the properties of matter. For example, matter is stable, as we know, and knots are usually more stable than a knot. Then it's the great time where more elements are being discovered, they are being classified. It's very clear that there's a great variety of different elements in chemistry, and there is also a variety of different knots you can build, and therefore different knots being associated to different elements kind of makes sense. And then there is a big mystery that nobody can explain, which are this spectral line, which could be explained here in this theory by the vibration of this vortex tubes. And so this is a very visionary theory when you think about it, about quantum knots, quantum entangled matter, and so on. And at the time, it caught the imagination of everybody. And you can clearly see the response from James Maxwell, who says, wow, this theory just satisfied more of the conditions of any atom which has been imagined as of now. And that triggers our third protagonist, Peter Tate, mathematician, to make the first table of knots. And so, of course, this was kind of simple. I presume he just took a piece of rope and tried to make different knots. As we've heard from yesterday's lecture on knot theory, it's not a trivial matter to make different knots and to actually be sure that they are different. Yet he managed to make a very appropriate table of knots, which is very remarkable. And what is interesting is that in his mind, he was not really making a table of knots, but he was making a periodic table of elements. But of course, in the following decades, quantum mechanics started to appear, the atomic structure vision completely changed, and then Lord Kelvin's idea of knot vortex completely got forgotten. But Peter-Take's table of knots gave rise to the whole field of knot theory. And nowadays, mathematicians have calculated billions of knots. Of course, they don't use physics of string any longer, maybe in some cases. And so we've heard already about the classification of knots, maybe just to make sure that everybody is on the same page, although I presume that everybody is familiar with this here. I'll just go quickly through it. So the simplest knot is the trefoil knot. Knots are usually classified using the number of crossings, which is the minimum number of crossings that appear when you project the 3D knot on a 2D plane. Pentafoil knot here, for example, has 5 crossings. This one has 7 crossings. And since they may be different knots with 7 crossings to differentiate all these knots, then we use this little subscript that says knot number 1, 2, 3, and so on. Then there is a related family of structure, which are links. And the nomenclature here is just the same. The difference is that instead of 1 entangled loop, which is closed, then there will be 2 entangled loops, or 3, or 4, 5. And so they are still classified by their number of crossings, but now we need to add this little superscript that tells how many cycles are entangled. So here in the example I chose to present, there are 2 rings in each of the cases, so they all have 2 as a subscript. So just as a comment, it was already mentioned in one of the talks yesterday, as chemists, we tend not to speak about links, we speak about catenanes for historical reasons. And as you can imagine, the synthesis of this type of molecule has started with the simplest one, which is the synthesis of this structure, because it has only 2 crossings. And therefore, although all the structures was classified as catenanes because they are all links, this one, in the mind of most chemists who are not really familiar with the field, will be mostly associated with the catenane. And so mostly when I will talk about catenane, I'm talking about what is known in mathematics as the hop link, and then I will name the other structures. There are the names like Solomon link and star link. And so I've told you how that the idea that knots and chemistry has been really correlated since the 19th century, but after the failure of Lord Kelvin theory, then chemists kind of lost their perspective on topology for almost 1 century, at least until the Second World War. And then after the Second World War, what happened was that people got interested in the synthesis of natural products. They developed a whole range of different synthetic techniques. They started to synthesize vitamins, all kinds of natural products. They got very comfortable with the synthesis of this compound. It's the rise of the golden age of organic synthesis. And then they started to get interested into synthesizing molecules that were not natural. And so, of course, it kind of made sense to think about the following question, which is it possible to tie a knot with a molecule? And it's a very audacious question because at the time, of course, it was not known that knots do exist in the molecular scale. They didn't know there were knots in proteins, in DNA, or anything else. And so just asking the question of whether it is possible to tie a knot with a molecule is not so obvious. And as I mentioned, the chemists started to approach this question by trying to synthesize what they thought would be the simplest topologically complex molecule to synthesize, which is the simple catenane. Because in everybody's minds, and I guess it makes sense, there is a correlation with the idea that the more crossing you have, the more complex is your molecule, and the more difficult will be the synthesis. I will show you actually that in latest year, this has proved wrong, and extremely complex, topologically complex molecule can be synthesized in very simple ways. But in the course of history, people have still struggled to synthesize molecules with higher number of crossings, and actually there is kind of a race of synthesizing the molecule with the most crossing. So Wasserman was the first one who actually proposed an idea to obtain a catenane. And again, this idea is very simple. You can imagine a molecular thread, which I've colored in orange here, has nothing remarkable in terms of chemistry, and it's just terminated by two reactive groups. Under a specific set of conditions, which are here on the screen, this reactive ends can close, and you get a cyclic structure. Now, imagine that in the same reaction vessel, you add a cycle that's already preformed. Then, statistically wise, the chances that this is threaded through the macrocycle at the moment when it closes exist. And therefore, it should be possible to get a catenane. As you can imagine, statistically wise, it's not a great chance of forming a catenane. And therefore, he performed the experiment, struggled quite a bit to isolate what he thought was a catenane, struggled quite a bit to characterize what it was, because they didn't have really spectroscopic methods to characterize precisely what it was. The characterization could not be done in a direct way. It was done in a very indirect way of material which was not really pure. Nevertheless, he believed he isolated the catenane in a yield that varied from one experiment to another in a range of 0.001% to 1%. So not that great. It requires about 10 grams of material to isolate 0.1 to 1 milligram of compound, not quite pure, and we don't know exactly what it is. And so there was an ambiguity on this experiment, but of course, it was the very first one, and everybody got very excited by this. And there has been actually an ambiguity on this experiment for about 60 years since it was performed, until last year. Last year, the group of David Lee of the University of Manchester performed again the same experiment. They managed to isolate the catenane, pure, characterize it with modern techniques like mass spectroscopy and so on, and they proved that Wasserman's intuition had been correct. It was indeed a catenane, and the yield they measured was very much in the range that was reported at the time, 0.07%. Still not that great as we expect. The yield has not increased over 60 years with the same experiment, but now we know, yes, it was a catenane. And so many people started to get interested into synthesizing catenanes, and they came up with all kinds of ideas to improve the yields, of course, because if a catenane forms with this low yield, you can imagine that the trefoil knot, for example, will statistically form in a yield that's pretty much zero already. One of the ideas, which is maybe the most clever, which unfortunately didn't work, is based on a Möbius strip approach. And many of you will understand what this is about. And to make it very clear, I have actually wrote the Möbius strip or Möbius strip 2B. So to build a Möbius strip, what you need is a strip. In this case, the strip is composed of two components. So the first strip here is in blue, and then there's a second strip in orange, and they are connected by this double bond which can chemically cut. So that's why I put this line in the middle. So now, a little bit like in Wasserman's idea, you have reactive groups at the end, which allow the molecule to react and be closed. And so the OH here, which I've colored, it doesn't show much, but it's colored in red, can react with this, which is also colored in red. And therefore you connect the orange part with the blue part, and what you get are two strips which are stuck to each other. They are here. Now, if you get this cycle to react with ozone, it acts like a pair of scissors, it cuts your double bonds, and what you get, there is not much surprise in this experiment, are two separated rings. Now, there is actually something else which can happen. You can imagine that the band may twist. I managed to twist it. Which means that if you connect the orange part which is here with the blue part, and then this blue part with the orange part. Then you introduce a twist. In the cycle, you form a Möbius band, a molecular Möbius band. And now maybe you have done this experiment as a kid or at an open day at the mathematics department. When you cut the double bond in the Möbius band, what you get is a different result. It doesn't separate any longer into two microcycles. It just separates into one larger microcycle. And what is amazing is that this actually happens. You see the yields here. The probability to form the two small microcycles is actually pretty much the same as the probability of forming the one larger microcycle. So twisting does happen. Where it becomes more interesting, of course, is if you have more than one twist. If you have two twists or three, then by cutting the line here in the middle, what you get can be either a catenane or a triple knot, or depending on the number of twists, more exciting structures. But this, of course, as you can imagine, never happens. That's the sad end to the story, a very sexy idea which actually never worked. And the reason, of course, is quite obvious. I already struggled to make the Möbius band with this. If I had to make two twists, I mean, you need something quite flexible, a bit longer than this. And so chances are that maybe this is too short. The probability to have more twists is also lower. And the more twists you have, of course, the higher is the energy of your system. And so the more it becomes, again, from an energy point of view. And so actually, this was very unlikely to happen. But this experiment triggered even more interest in the field. I mean, you can see how much creativity people put, how much effort people put in the synthesis of the structures, to the point that in 1971, Gottfried Schill wrote an entire book, which is here, on catenanes and knots. And I remind you, at the time, none of the structures were actually synthesized, and yet he managed to write a whole book about how you could possibly access all the structures. And that's actually a book which is quite highly cited in the field. I suspect it's a book that nobody has ever read or opened. I found it because the university library wanted to throw it away, and I was like, oh, wow, I saved it. For me, it's kind of a piece of museum, but it's actually quite rare to find. One of the ideas that he put up in his work and in this book is that if we want to form entangled structures, we really have to force the system to do so. There is no way you let statistics do it. And he introduces an idea, which is the idea of using the template, which he tried to use unsuccessfully. But 10 years later, somebody else came up and used this idea with great success, which unlocked the field. So what happens is in 1980, so quite a few years later, Jean-Pierre Sauvage at the University of Strasbourg, who was mostly interested in inorganic chemistry and copper complexes, learned that everybody was trying to make catenanes, and he thought, oh, maybe I could use my knowledge to make one. And what he was very familiar with is that if you take couple one and phenanthroline, which is a rigid ligand with two nitrogens, then it forms a tetrahedral complex. And if your chemistry days are long gone, the only thing you know is that this phenanthroline, just you have two units of phenanthroline, and because of copper, they get organized in a 90-degree angle relative to one another. You don't need to understand much more than this. And this is the idea he used to make the first catenane efficiently. The idea is the following. He first built a cycle that includes this phenanthroline unit, and then added copper. Copper binds to phenanthroline, but the problem here is that it would like to bind two phenanthrolines, but the cycle, it's quite congested in its environment, and it's very difficult for two phenanthroline to come around the copper center. But now the situation is a bit different if you add the second unit of phenanthroline as an open linear thread, because the thread can go through the microcycle, then you form your tetrahedral complex. As you can see, they are nicely oriented with this 90 degrees relationship one to another. And the orange structure is really threaded through the macrocycle. It is terminated by two reactive ends, which can react with a linker to form a closed structure. Now you have built your two rings, one around the other. You just need to remove the copper metal, and there is no longer any chemical bond between the two rings. Nothing holds them apart from this mechanical bond you have generated between the two rings, which cannot get apart. And so this is the whole idea of a template. The template is basically, in this case, a metal ion. It is used, you add it in the beginning of your reaction to pre-organize your components. You build your structure around this pre-organized component. Once you have built your structure, you remove your template. There is no trace any longer of the template, but yet you have formed your structure. Just a few years later, the same team expanded the idea to build the first molecular trefoil knot. They used the same metal templated idea, but now they build a thread, which is here. Normally they are colored in different colors, but it doesn't show. But hopefully you can still see the two threads here and there. Each of the thread has now two phenanthroline units here and there. And therefore what you form by adding copper is a double helix, which gets organized around your couple units. In chemistry, we talk about helicates when we use metal to build these helices, but essentially it's just a technical word. Helix just word as well. At the end, you still have your reactive group, which allow you to close the helix. And then when you remove the metal, what you generate is a trefoil knot. And so that's interesting because it suggests that this is the strategy that you can generalize to synthesis of other structures. If you form a double helix around one metal center and you close it, what you generate is the simple catenane. If you make a longer helix that falls around two metal units, what you generate is a trefoil knot. If you now make a helix with three metal centers, you generate a solenoid link, and so on. And so this strategy is supposed to be really generalizable. Some things to note, which are quite interesting, is that every time you add one metal center, you generate one more crossings. So you go here from 2 to 3 to 4 to 5 to 6. And when you move from an odd to an even number of metal, you go from a link to a knot, a link to a knot, and so on. So that's very, very nice. Problem is that there is an issue with this because we are using, as I mentioned here, linear helices. They grow in one dimension of space. And this means that as you add more and more metal centers, the distance between the ends that you need to connect becomes greater and greater. And that's an issue for an obvious reason. If you look at the pentafoil knot, the chances that you can connect these two ends are of course lower than just connecting the two ends which are very close in space. And very sadly, if you connect these two ends and you remove your metal center, it just unfolds into the knot. So it's a lot of work to do nothing much interesting. And so the team managed to make catenane, a trefoil knot, solenoid link, and then they never managed to go further. They never managed to make the pentafoil knot. And that's kind of interesting to realize that for about 30 years, it stayed very difficult to do anything bigger than the trefoil knot. Yes?
Can you control the tenderness?
Yes, so you can. So there are examples where very simply you can introduce a chiral center somewhere in the backbone, actually by Jean-Pierre Sauvage himself, and then you can control the handness.
How do you do the metal center?
So in this case, I don't remember well how it is. I think they use different strategies depending on the structure. But mostly you add something that coordinates copper better than your ligand.
Remove the metal center, so it doesn't affect the crystal structure of the initial.
Of course, so usually the crystal structure is more difficult to get when you remove the metal centers. So very often what you will see in the field when the synthesis of metal templated is that people will give the crystal structure before demetallation because it's very rigid, of course, heavy atom, facilitate crystallization, fractions. and then later they remove the metal. But of course, once they have the crystal structure of the methylated species, there is no ambiguity as to what they have made. If the mass after removing the metal is still good, then there is no ambiguity. Okay, so for 30 years, everybody was really looking at this example from Jean-Pierre Sauvage saying, wow, this is just terrific. But then nobody could really make much out of it because the synthesis, the strategy had this limitation. Then in the early 2010, the group of David Lee in Manchester got interested in the question, and they actually managed to solve the issue that Jean-Pierre Sauvage encountered. So almost 30 years later. And their strategy, which proved a lot more generalizable, is summarized in this review, which was published in 2017, if you would like to have more information. The idea is to replace linear helicates by cyclic helicates. So a cyclic helix is basically you take, in this example, 3 threads, and they form a helix around metal centers that connect basically the corners. And so it's still a helix, it has a different geometrical property, and the idea is still to connect the ends of this helices to form the knotted closed structure. But here what is interesting is that when you go from small helix, which has 3 threads, to the one with 4, 5, or 6, you see that the distance between the ends you must connect does not increase. Actually, in some cases, it looks like it decreases, and so the connection becomes easier. And so in principle, and it happened to be correct, it is possible to generalize this strategy by building different type of helicates, then you can make all kind of different knotted structures. Of course, it's still possible to misconnect these ends. Here I show an example in the cartoon representation. In the case of us wanting to build a Solomon link, we need to connect these 2 ends here. And of course, it's possible to connect these ones here, which unfortunately yields the knot, or these ones, but you see here, in this case, the distance is greater, is a bit more unlikely. Nevertheless, if it happens, it still yields quite exciting structure, and so why not? So the first example that the lead group reported was based on prior work which has been performed several years earlier, and it was known that this, or a slightly different version of this thread, was able to assemble around iron to form a pentahelix, so 5 threads. So here we're using a different metal, it's iron, the geometry is different, this is an octahedral complex, but the idea is the same, the metal is still here to pre-organize your system, it acts as a template. So here, your thread is terminated by an oxygen here, this is weakly coordinating to iron, not the greatest, and actually, when you only use this thread, the helix does not really form, but when you add this linker here, which is an amine terminated by 2 NH2, there is a condensation that happens here. This replaces the oxygen by nitrogen. Iron is very happy to have 6 nitrogen around it. The coordination is just perfect. This happens, all the 3 elements, the metal, the linker, the threads fall into place, and you self-assemble this structure, which, since the ends are connected here, happens to be the pentafoil knot. So again, iron acts as a template. This is what we've seen before. What is interesting here is that you need to use iron chloride in the reaction. Any other iron salt does not work for the reason that chloride itself binds to the cavity of the knot and also acts as a secondary template. And so here you have actually 2 templates effect built one on top of the other. But that's not really relevant here. What is important is that the strategy using cyclic helicate works, and it can be generalized. And so a few years later, the same team reported the synthesis of a Star of David using a very simple, a very similar strand that now form a hexahelix. At the end of this hexahelix, they appended reactive double bonds, which can react together using this catalyst metathesis to form the closed structure. So yes, it is really generalizable and it works very well. The strategy in itself is of course still limited. You cannot do any helix you want, of course, but you can combine this idea with other ideas to build all kind of more exotic topologies. And so I've selected only one example here to illustrate this, which is based on the Vernier system. And so physicists will be very familiar with this Vernier system. The idea is that you take a periodic system, like for example, of sets of different lines. You take two periodic systems which have different periodicity, superimpose them, and what you get is a new system with a different periodicity, which is the lowest multiple between the two periodicity of the individual system. And that's the basis for Moiré patterns and all kind of interesting phenomena that are of interest for physicists. But you can apply the same idea to chemistry. The approach is a little bit different. So you can imagine a molecule which has 4 different sites, which are identical. I colored them with these red circles. And then another molecule which has 6 identical sites, which I label with these little blue spikes. Now, each blue spike binds one red circle in the way which is here. And you can clearly see here from the complex, which is formed by reacting one red component with one blue component, the periodicity doesn't match. One has a periodicity of 4, the other one has a periodicity of 6. And so it's not possible for all the red and blue component to meet. And therefore what you will form is a complex with periodicities, the lowest multiple between 4 and 6, that is 12. And this happens when you form the 2 to 3 complex. Now all the binding sites are occupied. How do you apply this to the synthesis of knots? Well, here's a thread that was synthesized by the David Lee group, where you have basically 4 sites that can complex lanthanides, but each lanthanides only complex 3 of these units. And so there is 1 unit here which remain unbound. And so here again, you see the mismatch in periodicity between lanthanides that want these 3 binding sites and the thread which has 4 binding sites. And this means that if you add 3 threads for a number of 4 lanthanides, you will form 3 times this component. You still have 1 lanthanide left, and these lanthanides will just bring 3 of these components together. And then here you have double bonds that, just like before, can be closed to generate the closed structure. And now you obtain a composite knot, which is actually a mixture of 3 trefoil knots imbricated into one another. So quite remarkable how you can mix this helix strategy with other ideas to really build the complexity. And you can really see how topological complexity has increased over the time span of 50, 60 years of history. Now, these 2 strategies are clearly the most important strategies because they prove to be reliable. It doesn't mean that nothing else happened in the time course of 40, 50 years. On the contrary, many other syntheses were performed. One of the most iconic syntheses which has ever been performed was done by Fraser Stoddart, where he took 2 different molecular components that undergo condensation to form this macrocycle. And then upon addition of zinc binds here and there. But sadly, zinc would like to bind 5 nitrogens, possibly, and not 3 or 2, but 3 plus 2 makes 5. And therefore, if more macrocycles come around the zinc center, then it can template the formation of what happened to be a bromine link. So extremely impressive synthesis, which happened quite early on in the years 2000. It's really an iconic example, but is kind of an isolated case. There has never been any strategy behind it that proved generalizable like the other examples that I showed you before. All right, so basically to summarize this, the big trend as of now is to use metals as template. You take molecular threads, add the metal, it pre-organizes your threads, and then you form your knot. And this is the most common strategy to make molecular knots. Now there are other strategies which have been used. For example, you can use metal as a linker. imagine you have your thread, but your coordinative unit here is at the end, it binds your metal. And so you start to form an oligomer where you have every time one thread for one metal and so on. The advantage here is that the bond between the metal and the thread is highly reversible. And so you can form all kinds of structures and the system can organize, disorganize, reassemble. Eventually you will form the thermodynamic product, which is the most stable. And so there is some kind of interactions between the threads that promote the entanglement and the formation of a knot. Then you may form all kind of topologically interesting structures. And one of the great masters of it is Makoto Fujita in Tokyo, and some of the examples I will show have already been shown yesterday morning, but I will look at them from the perspective of chemistry rather than the perspective of mathematics. And so here what you see is a molecular thread, which is basically a very simple peptide sequence, just a few glycine units, no chiral center, nothing too fancy, but it's terminated by two pyridines. Pyridines are very good at coordinating silver. So you mix these two components, wait a little bit, and then what you form is a 7-1 knot. This is pure self-assembly, meaning that you don't have to do anything. The system just does it on its own, but it relies on different features. So the angle, so this is one of the pyridine coordinated to silver, coordinated to another pyridine. So you see that the coordination angle is 180 degrees. Then the peptide threads around the metal center. There's a positive interaction between the double bond or the oxygen here and the metal. All this are very weak interaction. It will be very difficult to predict the outcome of the reaction. But when they combine together, they bring all the pieces together into these fantastic molecular structures. What is even more remarkable is the structure forms quantitatively. And you can imagine that, so this is basically 7 threads and 7 metal, but you could potentially form a compound with 6 threads and 6 metals, or 5 and 5, or whatever, any other combination. In principle, they would be possible. They do not form. What is even more impressive is that this thread is directional. It might be difficult to see, but look, if you look at the pyridine here on the left and you start reading the peptide sequence, the first thing you encounter is a C double bond O. But if you look at the pyridine on the other side and you start reading the peptide sequence, the first thing you encounter is an NH. So one side and the other is not equivalent. It means there is a direction. If there is a direction combining 2 threads, you already have 2 possibilities, which is parallel and anti-parallel. If you combine 7 threads, now there are 40 possibilities to form this knot. Only one of these 40 possibilities does happen in the tube. So quite remarkable. And the team has expanded, of course, on the strategy. Why use glycine? You can use any amino acid you may like. And of course, depending on the sequence of amino acids, their rigidity and all kind of features, then you start getting all kind of different interesting structure. This example was shown yesterday. It's also by pyridine strand with different prolines here. And what it forms is this absolutely outstanding entangled sphere, which is a link. It's composed of 6 rings, which are interlocked. It has 24 crossings. As far as I know, this is the structure with the most number of crossings, which has been synthesized to date. And so here, the synthesis is equally remarkable, maybe even more, because look at the reaction time. Can you imagine the thermodynamic pathway? Yesterday was discussed the thermodynamic pathway for protein folding. This is in some sense relatively similar. How does the molecule find the way to get entangled like this? Well, it does very easily. It takes 2 minutes for this to happen. You just mix your components and you just have enough time to write to the NMR to see it. It's already formed. So quite amazing. What is interesting is that you start having potential features of interest for applications. So this structures as a cavity in the center. So it's like a virus structure, if you will. And as it happens, this amino acid here, all of them coming from the different threads point towards the center of the cavity, which means that you can change this alanine here for different substituents and change the size of the cavity in the middle to encapsulate different guests. All right. So the problem, as impressive as Fujita's work is, the issue with it is that it is absolutely unpredictable. I mean, the team has decades of experience in this type of self-assembly. Of course, as many chemists, we rely on our chemistry intuition to make this type of system work. We don't just do it from scratch. But intuition doesn't always work, and so it is difficult to see how many PhD students were actually working on this type of things before one of them worked. Presumably like 1/10 or 1/20 works, and the other one just nobody knows what happens. And so the issue here is that it is not predictable. And of course, we would like to build a system which have all the advantages of self-assembly, happening very fast and very well, but be a little bit more predictable. So maybe one way to do it is to use units which are a bit simpler than peptides, because of course peptides are quite flexible. They can form hydrogen bonds, all kind of weird interactions that are difficult to control when you combine them. But if you build simpler systems like from rigid aromatic units, then maybe there is more level of prediction. And so the group of Jin in China has extensively worked on self-assembly techniques. The principle is pretty much the same as what I've told you before in the case of Fujita's. The metal center is different. This is rhodium chemistry. And it allows you to combine different building blocks. So here you have two building blocks. They are combined in alternative ways. So one building block here, A, combines with B on each side. There is a different angle of 90 degrees between them. And now what you're using are just flat aromatic units, so they can stack in ways that we can relatively understand, not that well, but you can change a lot of parameters now. You can change the lengths between the pyridines, you can change the angle between the pyridines, and you can investigate how these effects can yield to the formation of different topologies. In this particular case, what they got is an 819, 18 knots. Quite an interesting topology. And when you look at it, you see how the aromatic units are very nicely packed and stacked on top of each other. So here, clearly, the geometry of the system is key in what's going on. All right, so to leave some time for questions and maybe a small break, I will close it here. I'll just recap quickly that there are two main approaches to make entangled molecules. The first one relies on metal temptation. This is the main approach which has been undertaken until now. The other approach, which has been literally exploding in the past 10 years, is to use metal as linkers to form what is called metal knots. But of course, this raises the question as to whether it is possible to make knots in the absence of metal, because I only showed you molecular knots that rely on the use of metals. And so is it possible to form knots in the absence of metals? Yes, it is, but actually this is the field of research which is a lot less developed. Of course, it presents advantages because not every functional group is compatible with metal coordination. And so eventually, if you could build molecular knots in the absence of metal, you could really expand the palette of chemical functionality that you could introduce inside the structures. And so I've just selected one example to close this lecture of a knot which was synthesized in the absence of metal. Most of these examples were just discovered by serendipity. There was no expectation to form a knot, but the knot just formed at some point, and people just were puzzled by the apparition of this knot. And so in this case, the group of Chris Hunter in the UK was just trying to build microcycles from this condensation of these two components. And they formed a structure that was relatively big. The spectroscopic features were a bit off, and so their interpretation was that they had formed this 2-catenate. As it happens, almost 10 years later, another group performed the same experiment. They isolated this catenate. They managed to grow a crystal that was diffracting. And as we have mentioned before, having the crystal structure in the absence of metal can be very challenging. And so they were very lucky in that sense. And what they discovered when they saw the crystal structure is that it was absolutely not a hop link, but actually a telephone knot. Even more exciting. But impossible to predict. And so sadly, all the synthesis in the absence of knot have remained like very niche, one here and there, and they have not yet fulfilled their potential. Okay, so on this, I'll just close again, recap, possible to build knots by metal templation. The advantage here is that via this strategy, you get a great level of control because you understand step by step how you assemble your components. The drawback is that the synthesis are very demanding. It takes several months to several years to design your system properly, build it, characterize it, and so on. And so there are challenges here. When it comes to the synthesis of metal and knots, the advantage is that the strengths are a lot easier, usually quite easy to synthesize, so you can screen different strengths very easily. The drawback is that the syntheses are completely unpredictable. You need to play with luck. And something which may be an advantage or a disadvantage, depending on how you look at it, is that the metal ligand bound is very reversible. And so that means that when you form the knot, if you change your experimental conditions like temperature, solvent, or whatever, it may just completely fall apart. And then the synthesis of organic knots that do not rely on metal, as I've said, not much is done. And I will close my talk here because this will be the topic of my research talk after the break. Thank you for your attention.
Thank you for this wonderful overview, which I think was very appropriate for the broad audience we have. And
I try to do my best to keep it not technical.
Okay, so questions, please.
Okay, so now the second part of this talk relates. I don't know if I'm standing on the way of some people. That's okay. Relates to our own research, and so we are interested in the synthesis of molecular knots, of course, which has become known as the field of molecular topology. And as it was mentioned before, we work in Finland at the University of Jyväskylä, which looks pretty much like Hokkaido in winter time. And so in the previous tutorial lecture, I hope I've conveyed the idea that over the past decade, the topological complexity which has become available has grown tremendously from the synthesis of the very first defoid knot by Jean-Pierre Sauvage to nowadays the synthesis of entangled materials. And so there are still challenges in the field which I've pointed earlier, notably in terms of synthesis. But okay, but as the technical challenges of the synthesis are slowly being solved, all these issues are being solved, then one question which I have not mentioned until now arises is what these molecular knots can be useful for. It's actually quite interesting to point out that the field has never been driven by any idea that molecular knots would be of any use for anybody. It's been purely driven by curiosity, which is quite unique and is quite difficult to do in the modern landscape of science, where we always ask to justify when we write research grants why we want to do this. And so this field has been preserved kind of by its appeal in topology, I suspect. But now comes the question, what can we do with this molecular knots? And there are different groups which have tried to do things with molecular knots, but it's quite sparse here and there. And here, perhaps your contribution will be very welcome because you may bring a new perspective and make all these molecules useful for your own field. So this would be very much appreciated. But of course, I have my own idea of what could be the use of introducing topology in not yet molecules. And one idea relies on the parallel between chemistry and biology. So we've had yesterday a beautiful introduction on protein foldings and protein knots. And we know by now that primary sequence of proteins induce its folding into the secondary, tertiary structure, and then the assembly of the quaternary structure. And here I take the example of protein. It's very important to keep in mind that when we look at protein tertiary and quaternary structure, that these are not static conformation. They are dynamic structures. They can respond to different stimuli. And when they change conformation, it modulates the activity of the protein. In some cases, it completely changes the activity of these proteins. And us as chemists, this is a property that would be very useful. We could imagine building very long polymers or macromolecules, which would very precisely fold into conformational states that are well defined, just like proteins, but would be able to change conformation, and as they change conformation, they will have different properties. But this has proved to be impossible to do. As molecules grow bigger and bigger, we tend to be not able to control their folding, and therefore we cannot do much with these macromolecules. And here comes topology, because when you tie knots with molecules, of course, you reduce the conformational freedom of molecules, and therefore it should, in principle, become possible to block them into conformational states, which could, for example, resemble the tertiary structure of proteins. So here I take the example as a cartoon representation of a link, which is multiply entangled and is blocked into a conformation that looks like two alpha helices connected to another, just like a surface. But of course, the threads are not connected by any chemical bonds because they are just entangled, which means that they can still move relative to one another. And that means that these knotted structures can be deformed. And so in principle, they can adopt different conformations that may have different properties. For example, you may think that this structure can catalyze the reaction from A to B, but catalysis would be switched off in these cases. And if you're familiar with knot theory, then you will know that knots can be deformed in many ways, which means that in principle, you could have 10, 20 different conformations with the same molecule. And all of these conformations could have different properties. One of them could catalyze the reaction from B to C and whatever. And because they are closed entangled structure, it's not possible to unfold them. And so they are stuck in these different conformational states, very much like proteins somehow. But how do you build the structures? So of course, that's not trivial. I showed you that the synthesis of molecular knots is not trivial. The main strategic approach relies on the use of metal templates. And here comes a drawback, as that when you pre-organize your thread using a metal, at the end of the synthesis, you have to remove your template, and this generates a void space, and it loosens your entire structure. That's the reason why they are more difficult to crystallize. And so here you have actually no definite shape. And so you can't really use topology to block the conformational state of your molecule. So this is presumably not the way to go. Now, if we look at metal and knots, I've told you that the bond between the metal and the ligand is quite reversible. They tend to fall apart quite easily. And so, of course, it's difficult to induce conformational change if, when you change the experimental condition, you not just fall apart. And so, presumably, also not the way to go, which means that these structures can only be obtained by synthesizing purely organic molecular knots. And as I've mentioned before, these knots are the most difficult to synthesize to date. And so this is what got us interested in the synthesis of knots, the metal-free synthesis of knots that do not rely on the use of any metal of any sort. And we've actually designed a system which you can arguably say is the simplest ever system to synthesize molecular knots. Even undergraduate students who have absolutely no experience in chemistry or topology can make this molecule in 1 week when they come to the lab with really no experience. So what we do is that we use the hydrophobic effect as a driving force for folding. We know from biology that the hydrophobic force is great for folding, and it has already been shown previously by several groups in the world that hydrophobic effects can be used to promote the assembly of structures like the simple catenane. And that suggests that, of course, you can build more complex structures using the hydrophobic effect. And so what we did is that we synthesize different building blocks like these ones, which are very simple. They can be obtained in one step from commercially available compounds. So you just order them, It's really baby chemistry. You mix two components together, hit the reaction mixture, some point it precipitates, you filter it, and that's it. You get your building blocks. No other purification needed. And you see they are very hydrophobic. They are composed of aromatic units, but they are water soluble because they have, in this case, for example, permanent positive charges which allow for water solubility. And so here in this case, one is dialdehyde, this is the aldehyde function, and one is a hydrazide. It is already well known that aldehyde and the hydrazide can react together to form a condensation compound, and the bond between these two components is reversible, just like in the case of metals. And therefore you can open it, close it, and you can generate mixtures of compound. And at some point, if one compound is more stable than the other, then everything will converge towards the thermodynamic minimum. And so there is clearly an analogy with metal and nuts, but just we don't use metal as a reversible linker. Now we use a covalent bond, which is itself dynamic. The advantage is that covalent bonds are dynamic, but they are more robust. And this specific bond, the hydrogen bond, is only dynamic in acidic conditions and high temperature. If you change the pH and you lower the temperature, it's perfectly stable, it's very robust, which means that you can isolate your structure, crystallize them, characterize them, and so on. And so here in this specific case, how the experiment is performed is that you take your two components in blue and orange, dissolve them in water at a concentration of 5 millimolar total, adjust the pH to 5, heat up the reaction mixture. You wait, usually we wait overnight to be sure that it goes to completion. But in many cases, the reaction is finished much earlier than this. And then what happens is that the two components start to react together, they oligomerize, and then at some point, because they are so hydrophobic, and as they oligomerize, the hydrophobic surface in contact with water becomes very big, they tend to wrap around themselves, and what we form in this case is a trefoil knot. And interestingly, the synthesis of the trefoil knot is actually templated by the anion which is introduced at the beginning of the synthesis, which is bromide. And we see that the two bromine are bound in the central cavity of the trefoil knot. And so the yield of the trefoil knot depends upon the halide that you use during the synthesis. And so we tried different halides, and the best one is the biggest one, iodine. The yield of the trefoil knot in this case is 70%. For the other halide, the yield is lower. It just depends on the size. As they get bigger, it fits a little bit more loosely in the cavity, and therefore the activation effect is a bit less pronounced. But you see how this synthesis is quite easy. And what is interesting is when you change the central component and you replace this relatively large naphthalene by a shorter aromatic here, the outcome of the reaction completely changes. And then in this case, what you get is first you form a macrocycle. So this is the blue component here, linked by the pink component. And again, it's very rigid. Again, it cannot fold to minimize the hydrophobic surface area exposed to water. And so the system is kind of frustrated. And this drives the entanglement of the second ring around this one. This is not a trivial catenane. This is already a rather complex Solomon link with 4 crossings. But you see that it forms very efficiently here. So this is HPLC or chromatography, which basically tells you about the purity of the compound. If you have one peak, it means that you form only one compound. If you have 2 peaks, you have 2 compounds. And so it forms very efficiently because all the aromatic hydrophobic units are very efficiently packed, and the hydrophobic surface is significantly minimized during the synthesis. Therefore, this is the thermodynamic product of the compound, of the system. And so we've been playing with this by changing the geometry, getting all these different topologies and isolating them. As I've said, these compounds are stable when we work in normal conditions. Therefore, it's not only possible to isolate them, but you can also start to play with them. And so we thought this was already quite complex, not as complex as this highly entangled cartoon representation I showed you in my first slide, but maybe we could already test the idea of whether these structures can change conformation and how many conformation they can adopt with the Solomon link. And so this Solomon link forms this very well resolved conformations in water, again, because it minimizes the hydrophobic surface. But when you dissolve it in a different solvents, of course, things change. In acetonitride, for example, that's a solvent of medium polarity. It's clearly not as polar as water, and therefore the Solomon link can change conformation. And what we observed is that in acetonitride, it kind of open up a bit like a flower that blooms. All the the aromatic units just unstack, and then it breathes out. And this is just driven by the fact that the Solomon link tries to increase the amount of apolar surface with the environment, which is now less polar. And then it starts forming intramolecular hydrogen bond between the oxygens here and the neighboring NHs that stabilize this conformation. So I will not show you any technical data, but I just want to show you an NMR spectrum, so nuclear magnetic resonance. We don't need to analyze the spectrum. The only reason why I show you this is because you see that this molecule in acetonitrile has very nice, very well resolved sharp signals. And this indicates that you do have just one conformation, and that it's a very well defined conformation. Otherwise, your NMR signals would be very broad, or there would be multiple signals. Now, when we discovered this, we were a bit puzzled by this, the fact that the Solomon link had changed conformation in such a dramatic way. And naturally, what we thought is that if we were adding water in the tube where we record the NMR spectrum, then we would switch back to the conformation we had seen in pure water. And this did indeed happen as expected. And so here's the experiment. We just take the NMR tube and add a few drops of water, 0 microliters, 12, 20, 30, and then you see very neat switch, very sharp transition from one conformation to the other one. You see here at some point a mixture between the green and the purple conformations. And then after 40 microliters of water, you only have this other conformation. So you can really control the switching between the two different states. Now we were a bit puzzled by these quantities because we do the experiment in 500 microliters, and we see that 40 microliters of water is enough to converge everything into one conformation. And usually when the switch is driven by change in polarity of the environment, you need to add significant amounts of water, like 50%, 70%. And this actually only corresponds to 7%, which is very little water. And so this made us think that maybe the change in polarity was not the only driving force for these conformational changes. Maybe there was another driving force, and the most obvious driving force is that water binds, also acts as a template, which binds one of the conformations. And because the NMR signals are very neat, then we can use this, the NMR, the structural information gained by NMR to look into the thermodynamics and the kinetics of switching and gain more information on how the transition occurs. And so in this case, what we were able to demonstrate is that water binds to the Solomon link. The Solomon link actually has 4 binding sites for water, and these binding sites require 1 C double bond O and 1 NH. In the green conformation, the binding site is closed because they are just involved in a hydrogen bond with each other, and they don't care about what's going on with the rest of the world. But when you switch to the purple conformation, you break the hydrogen bond, and then the two components are now able to bind water. And so you have 4 binding sites, but they are interconnected. Either all of them are in an off position, or all of them are in an on position, and they all switch together because of the topology of the compound, a little bit like in a game of falling domino, because it's all entangled, and therefore if you open one binding site, you switch on all the other binding sites immediately. Makes sense. And so when we work in pure acetonitrile, the two conformations exist, of course, but this one is mostly unpopulated. We don't see it, we only see the green conformation. But things change as soon as we add water, because it binds in the cavity. Each of the binding sites binds one equivalent of water to the formation of two hydrogen bonds. So now you see why it is important to have both your oxygen here, which binds the hydrogen there, and the oxygen of water binds the other hydrogen there. And then this binding shifts the equilibrium towards the purple conformation. Now the binding is highly cooperative, we say, which means that either we see no water molecule bound, or we see 4 molecules of water bound, but we never see any intermediate state in which you have only 2 water molecules bound. And this fully makes sense because you can see that there is a network of different hydrogen bonds in the core, which stabilizes the whole system only if you have 4 molecules of water in the system. And this behavior is already very close to what we see in biology. If you remember your biology days, you may remember the example of hemoglobin. Hemoglobin is a large protein which is composed of 4 subunits, which are identical. Each of the subunits can bind 1 molecule of oxygen. The first binding to oxygen is quite demanding, but it induces a conformational changes that facilitate the second binding, which itself facilitates the third binding, and so on. And here what we see is a very similar system when we also have, it's a much smaller molecule, of course, but we also have 4 binding sites, and the 4 binding sites are highly interconnected, and therefore one binding event immediately facilitates the other binding events. And actually, this is an example of almost perfect cooperativity where you just see either 0 molecules of water bound or 4, as I said. Now, if you are interested in the mathematics of not theory, you will be a little bit disappointed by this conformational change I showed you, because we start with a molecule which has a C4 symmetry, and when it changes conformation, it conserves its C4 symmetry, so it's relatively small in terms of amplitude. And you can see beautiful cartoon representations of knots undergoing what is called Brigg-Meister's motions, where you can really move all the threads and completely change the shape of your knot. Can it happen in this case? Well, the answer is yes. This molecule can also undergo much larger conformational transformation, but of course you need to find the right conditions in terms of solvents and so on. And so here we recently discovered that in a different solvent, methanol, upon addition of sulfate, the molecule undergo this quite large conformational change. It adopts now the D2 symmetrical conformation. It's a bit difficult to see on the molecular structure, but if you just look at this benzene unit here, which is nicely sandwiched between the 2 aromatics, so inside really the core of the structure, you see that it happens to be completely outside, very, very far from its original position in the second conformation. So you have really distorted your molecule. And this enables the formation of a cavity where sulfite fits very nicely, it binds, and we actually have 2 equivalents of sulfate. Here again, the binding is cooperative, which means that the second binding event happens a lot more easily than the first one, and this is very counterintuitive, because this time, unlike water, sulfate is charged. It has 2 negative charges, and therefore intuitively what you would think is that the first binding will occur, but then the second binding will lead to Coulombic repulsion between the 2 anions, and it would actually be less likely, but this is not the case. The second binding actually occurs much better, which is very counterintuitive. So now, what's next? So these are quite interesting structure. You see that we start playing on the conformation and see if this could yield interesting structures. We're quite happy with this type of synthesis because they're, as I mentioned, super easy, very easy to do in the lab, even only with the help of undergraduate students. We were very happy because we got quite complex topologies from a system that is very simple and that does not involve metal, which I've said before was challenging. But then we are also a bit disappointed because we see people like Makoto Fujita making these beautiful knots, and we see no reason why we would not be able to make things a lot more complicated, of course. And so here arises some of the limitations of this current system, which are the limitations I've mentioned before in the case of metal knots. They share some limitations. The approach is very easy to implement, it's accessible and scalable, but it's uncontrolled. So we don't know which type of topology we will form. And I showed you two examples where we just change one component in the reaction, and in one case we form a Solomon ring, the other case we form a Pfeffer knot, and there is really no way to predict which one will form preferentially. Come back to your question. The structures are quite simple, symmetrical, and we would like to break this symmetry, and they have no obvious function because we were not interested in introducing function. Of course, we were just interested in tackling the scientific challenges first. But we would like to address all this issue. What we would like to design is a method which is still based on the hydrophobic effect, but pushes forward the analogy with protein folding to build larger structures in ways which are highly programmable, systematically predictable, and hopefully modular so that we can introduce different functional groups on the surface of these molecular knots, and hopefully build topological complexity from one step to another, like has been done by other groups. And the approach we want to do this is by making helices, because I showed you before that double helices are ideal intermediate towards the formation of knots and links. But instead of closing these helices like other people do, what we would like to do is to connect helices together. Because the advantage is that if you want to close the helix, you need to find a linker of a suitable size. But another helix can also be considered as a linker. Obviously, it has the same size because they are identical helices. And in one go, you double the number of crossings. And so this has obvious appealing features. And so what we've been doing in the past few years is learning a little bit better how to use the hydrophobic effect to build double helices. As I said, we would like to make a system where the assembly is programmable, and that raises the question, how do you use the hydrophobic effect to predictably assemble double helices? And here you will see that there is a direct continuation between what I've shown you and these helices. What we're building currently are molecular strands, which are composed of a hydrophobic core. It's supposed to be in gray, it's difficult to see the difference in color. And then you have hydrophilic ends, which are positively charged. And here, the sequence of this hydrophobic and hydrophilic components can predictably control the assembly of either double or triple helices. And I will just show you briefly in one example how this works. Conceptually, it's very intuitive and very easy to grasp. The idea is that you take your strand, you dissolve it in water, and then because of the hydrophobic effect, it will try to fold to minimize the hydrophobic surface area. This is very rigid, and therefore it can only fold into a specific conformation. And we know this conformation, it requires a number of 6 aromatic units per turn, and so we can easily model it. What happens is that when it folds in this conformation, it actually brings all the components which have permanent charge on top of each other. And so it does not reduce the hydrophobic surface at all. On the contrary, it brings all these charged components on top of each other. And this makes the formation of the trivial, simple single helix unfavorable. And therefore, it drives the assembly of 2 strands, because now what you form is a double helix. All the hydrophobic residues are very nicely sandwiched between the hydrophilic residues. They are shielded from the outside environment. And you see, if you look at the top view, that here there are only hydrophilic components nicely exposed. And so this is a very minimalistic system. So there is really nothing fancy. We only have 2 units in the sequence that program the assembly of the double helix. As I said, we can change it to control the formation of triple helices. We just need to change the number of the components and their positions. And what we're doing now is building on the systems to start building helices which are longer, introduce elements that will allow us to control the helicities, and then eventually introducing at the end reactive groups that will enable us to combine these helices together. So this is kind of a new language which we are learning step by step. Therefore, I will not show you any results yet, but maybe next time we meet, then I will show you how this works. And so anyway, this brings me to the end of my talk. There is still like 2 minutes for question. I would like to thank my lab members who are working very hard on making all this noted and entangled structures, and you for your very kind attention. Thank you.
Thank you for this wonderful second part of your lecture. Do you have questions?